Hello, everyone. My name is Nicholas Clark. I'm a mathematics major here at Texas Tech University, and today I'm going to be talking about my honors thesis entitled Exploring the Complexities in Atmospheric Boundary Layer Dynamics over Mountainous Regions and Their Impact on Tracer Distribution. Okay, so some concepts to understand this research problem and as to how we got to this research question is first, we need to understand the atmospheric boundary layer. And the atmospheric boundary layer is just the lowest 1 to 2 kilometers of the Earth's atmosphere that is directly influenced by the Earth's surface forcings. And one of those surface forcings you can see in this figure here, where we have a shallower purple region here, the nocturnal or stable boundary layer. We have a shallower boundary layer at this point because we have lesser incoming solar radiation and thus a lower surface heating of the atmosphere. And so we see a shallower boundary layer. And now this is different as sunrise hits and time progresses into the day, we see a deeper boundary layer. And now, so we see the boundary layer changes with time. So how this affects our trace gases within the atmosphere is part of our work here. And trace gases are just the gases in the atmosphere that make up less than 1% of its total composition. For example, water vapor, carbon monoxide, carbon dioxide, and methane, to name a few. And so a couple of things we need to understand about how the boundary layer depth influences these tracer concentrations. And that is first, when we have this shallower boundary layer, we actually exhibit greater concentrations in trace gases because we have a lesser volume to work with. And so during the day, when we have this mixed layer here, we have a dilution effect of trace gases and we see lower concentrations. Another thing to understand is that there's not a lot of turbulence that takes place during this time due to the lesser surface heating. And so we don't see as much mixing within the atmosphere. And so we might see instances where the concentration of our trace gases are greater near the surface layer as opposed to sort of this 500-meter range here, which is different to our mixed layer, which we expect to see a similar concentration no matter where we are within this layer. And so part of our work is understanding how do the trace gases within this boundary layer region, say this mixed layer, and this free atmosphere work. The free atmosphere is just the layer above the ABL. And so we want to understand how is this interacting with one another? How are the trace gases interacting with one another over complex terrain? And this is where the second part of our work comes into. And you can see, if you look at this figure here, that our CBL, our convective boundary layer, which is just another name for the mixed layer, the green region from before, we can see how it changes spatially over the mountainous regions. We have shallower boundary layers over these peaks and sort of deeper in the valleys. And so part of our goal is to understand how do trace gases change, how do the concentrations change over mountainous regions, and more importantly, how do they interact with the free atmosphere above? We want to look at gradients between the two. And the way we do that is by using this Act America campaign data set. The Act America campaign was a flight campaign that took place between 2016 and 2019. And they took place over 3 regions. The region we'll be most interested in is this mid-Atlantic region because of the presence of the Appalachian Mountains. And there were 2 flights. The one will be most important for the understanding in this presentation is the B200 flight. And so basically the way it works is we have a B200 flight that is flying really close to the Earth's surface to to measure the trace gas concentrations within the ABL. However, as we fly over the Appalachian Mountains, the B200 has to fly upwards to avoid the mountains for safety, right? And so it's at those points where we expect the B200 to enter into the free atmosphere above. And part of the research was trying to understand where these transitions into the free atmosphere occur. And the way we do that is by looking at changes in temperature or potential temperature. And this is because at the top of the atmospheric boundary layer, we expect an inversion to take place, which is a drastic increase in temperature with height. And so all we have to do is look at changes in temperature with time and see where we see greater changes. And it's at those points where we mark our transitions. And then we just need to take a mean a mean profile of the tracer concentrations at the in the free troposphere and within the AVL. We subtract the two, and we get a gradient across the two, and we can understand what's happening. And these are the results we found, and they're actually very compelling because we actually see a lot of what we expect over flat terrain. However, with a caveat, and that is that we see a lesser concentration that we might see over flat terrain. And so going forward with this work, we want to better understand what is causing this lesser correlation and within these complex terrain, and how can we better understand those mechanisms. And so, yeah, this is what I did for my honors thesis. And yeah, thank you everyone for helping out. And yeah.